So let's wrap up the first part of the slides by quickly looking at an example here, which will show a few different things. So we've got a heat exchanger here. We want to drive the maximum temperature at the outlet to be 30 degrees C, and we want to adjust the wall temperature of the cooled pipes. We'll do it every 5th iteration so that we give the flow a chance to settle down. We don't want to do things every iteration, because that has a tendency to be rather lumpy and maybe not quick to converge. So what we can do here is we can adjust the wall temperature. So we can start with a guess, and then we can adjust it so that based on our target difference and a relaxation factor, and so hopefully as these two get closer together, we will be adding a smaller and smaller change to this, and it will converge. And we'll do it every 5th iteration. So what would our expressions look like? Well, we've got some inlets. So we've got our inlet air, our target temperature we want for the outlet. We want the starting temperature of the walls. Let's do a relaxation factor. We need a heat transfer coefficient to put heat into the flow based on the wall temperature. In this case, it'll be going out into the cold pipes. Now, we want to do things every 5th iteration. So we can say here that if the modulus of iteration and 5, so that will pick out 5, 10, 15, 20. If that's greater than 0, switch it to 0. But if it's 0, make this 1. And the nice thing is we'll be able to plot that in a second. This is the maximum outlet temperature that we're shooting for. So the target we want is the maximum static temperature at the outlet. This is what the external temperature needs to be on the wall. If we've got the surface heat flux, then we divide that by the heat transfer coefficient. That gives us the delta T. We add this one on the right-hand side to get the T external. We can get an area average over the tube of the temperature. We can set up that equation for adjusting. And we can set an if statement here so that if it's before the first 5 iterations, then this exit external temperature is set to be a constant, and after that it becomes this adjusted one. So we've got all our variables in here. We can go through the expression manager, checking them and setting them up. We can test, for example, that we've set this up right. So we want to make something non-zero every 5th. It's also going to have 1 there. So 5, 10, 15, 20, etc. So we've got our logic right. We can go in here and put a heat transfer coefficient in here rather than a number, so that we're actually using the expression that we've got. We can put the free stream temperature that we're going to calculate in here in this convective boundary condition on that wall. We can create a surface report with this, and we can have a look at in an expression report where T adjust is going to be plotted. So this is just a standard one we're going to create without using expressions. Here we're going to create one using an expression just to be different. Now we're setting those up to go into files, etc., the data. So if we solve the flow with localized scaled residuals, So the flow converges down really nicely. Obviously, the energy equation is very lumpy to start with because we're making adjustments which throw the residuals off. But as we get closer and closer to convergence, those adjustments are getting smaller, particularly as this height might be constant, but it's on a log scale. So it's actually getting smaller and smaller. This is what the Tmax is. The black line is being plotted. This is what the target was. So we can see it's coming down. This is what that external temperature has to be. And then we can see what the adjusted temperature is here and how it's actually flattening out to a constant value. And that's our final solution. So you can see in that example, it's quite possible to do even simple logic in these expressions now. So I'm in Fluent here. I'm now addicted to the dark mode. So I'm going to pull in a CFX setup. So unfortunately, these panels are coming up on my other screen. So I'll just quickly do an import there. Actually, let me move this across a bit, then they'll come up here. So files, import from CFX, the results file. So let's have a look at what's coming in here. So once it's in, we can go here and quickly have a look. So we'll just quickly display that. So this is a column. It's a simple bubble column. So I'm going to use this to demonstrate a few things that I might want to bring across. So what I've done is I've gone to my setup of this, and this particular case has all of those expressions in it. So I might want to bring some of those across, ultimately all of them. So let's have a look at how we might go about doing some of those things. Now, in order to make this easier, what I'm going to do is, instead of just reading in the base there, I'm going to go to a case file and read in a case file. Now, what all I've done is import that, and I've set up the basics of the model in here so that I've got various models set. So if I look into here, I've got multi-phase, I've got a turbulence model set, etc. Because I want to be able to use this. Now, if I weren't doing a webinar, I'd have both screens working super hard now. But here we're going to do that. So I'm going to bring up the manager. I'm going to drag this away so it stops covering this. And we'll first of all create a new expression. So we're going to have to keep bringing these things back. So let's do something simple first. So all I have to do is highlight, Control C, Control V. Won't paste into there, my mistake. We'll paste into the other. So let's then pick up something with units. Copy, stick it in here, paste. Now if I hit return, invalid syntax because I missed copying that. But you can see I can quickly get that done. I could give a name to this now, but I've already got a named expression here. So that one's ready to go. I hit OK. And now in my expressions, I've got one. So let's try something a bit more complex. So let's just bring in something that's, say, got an if statement in it. So let's just drag this one across. So I'm going to copy that. I know that that's equal to my J parameter. So I'm going to stick it in here. do a Control V. I need to hit Enter to jump down. Now, this has got an invalid syntax. So very quickly, if you've been doing this, you know that the if statement is slightly different. It's just in capitals, especially if you're a Python user. So Enter. That's invalid because H is not defined, but that's okay, because we're going to want to define that later. So we could, if we look here, we can start bringing things in. Now, you'll notice on here that there's something called bubble slip, and that is some sort of magnitude of the slip velocity, and that takes me 4 lines here to set that up. So how am I going to do that here? So what I'm going to do is create a new one. Now, I'm going to call that B slip. So what I can do now, the reason I wanted to bring this in with some basic setup is I can go down and say velocity. Now I can choose. So if I just want magnitudes, I can bring them in. But if I want to, I can bring in a vector. Subtract from that, variable. Where's my velocities? Velocity. I've got the water one. I want my bubble one here. And OK that. So I've now got a vector there. If I want the magnitude, I can create a new one, which is just mag of B slip. And I can go in here and I could go and get my expression, B slip, and I could just type mag. And that's an operator. So I could now put a description here. This could be magnitude of slip velocity. So you can see how I can start bringing these across. I've actually got rid of 4 down into 2. The nice thing is now I've got a vector field there automatically generated that I'll be able to use if I want a vector, if I want to do a dot product or anything. I don't have to do it longhand. Let's have a quick look at something else that might be interesting. Obviously, we would just work through doing these systematically. Yeah, look, we could do this one just to show another simple thing that needs to be done. So new, this would be inlet area of some pipe that we're not modeling. Otherwise, we would just use the area function. Pi doesn't exist. We just remember that that's there. I'd like to know how big that area is. What? Why can't I do that? In that area. So I should be, well, I can evaluate things once I've initialized. So we've got something here which has got dimensions. So you can see that as we bring these across, we build that up. When I'm doing this, I would be deleting these as I go so that I know what I had left to bring across. All of these really simple ones we could bring across in seconds. If we want to do something that is a little more messy here, so let's have a look at bringing across something like this. So we don't actually need the equal sign. So let's copy it. New. I'm just going to call that Yurtvoss. I'm going to paste it in. Now that's going to have quite a lot of issues. So let's work through. We know that water density is not going to look like that. We know it has to have a phase on it. So I'm going to backspace that, and then I'm going to go in here and say variable density, density of water. Now I've got that in. I want the density difference. So I want that ellipsoidal bubble density. So I'm going to delete that and go in here and use a variable density ellipsoidal bubbles. So I've now got my density. I might want my bubble diameter here. So I want that squared up. So what I'm going to do is go in here to my variables. That's a property. It's the diameter of ellipsoidal bubbles. Yeah. And that's all done. The only other thing wrong with this is sigma is not defined. So sigma was the surface tension. So let's quickly do that. And then we'll stop and go back and have a look at how we can interrogate these a bit more. So if I look down here, sigma's got some value in Newton meters. Copy, paste. You must hit enter. Okay. So let's then go back in here, close that, open this up a bit so you can see fully. I've got my named expressions here. So one of these is still invalid because we haven't finished bringing stuff across, but we could export those to a file. And then if I go into that directory, I will quickly refresh that. Well, where did I save that to? I know. I'm on the other screen 1 second while I grab this file and open it up and then bring it across here. So that is what this file looks like. We've got all of our setups in there ready to go. If we want to do things now, so if I want to plot some of these, I could, for example, very quickly make a plane. So let's make any old plane. Yeah, create, close. I could go to graphics, and I can't do anything unless I initialize with plots. So I'll quickly initialize because I need something in there. I'll just take whatever it gives me. And now I can do contours. I can edit a contour. And I could, for example, give it a false. Now that's coming out to 0 because I haven't got all the necessary stuff set up in the code. But you can see I can come down here. And actually, I don't need to create a magnitude if I want, because I can use that directly. So I did that just as an example to show you how you can make a magnitude. But if I want, yeah, and that's going to be here. So I think we're coming up to the hour. I just wanted to wrap up at this point. I don't know if anybody has any burning questions. If they have, if they've typed them into the chat, I can have a look now to see. Yeah, we can definitely share the recording. Can we store VOF and VOF gradient in expressions during a multi-phase flow? Simulation in Fluent. Yeah, the volume fraction will be in there, and I don't know whether we can get up the actual gradients that are being used. We'd have to have a look at that, but we should be able to get gradients. If not yet into an expression, then we could definitely do it in a user-defined memory. So, yeah. What I'm finding is that expressions are being more and more useful for doing things. And the beauty is I don't have to create any user-defined memory or anything to do that. So at this point, we're almost at the top of the hour. So I'm just going to summarize by reminding you that the expression language is now very powerful there. The whole Fluent experience has changed over the last few years. And if you're not using it, it's really time to give it a go. If you're a user who only wants to do basic CFD, then Fluent has a really nice Pro option, which has limited physics, but still contains the meshing, can go through and do flow, heat transfer, species, and has all the full expression language. And I think that is really key now. There's lots of things that you can do in expressions that directly allow you to set up problems. And what I'm seeing more and more is that you can use expressions to eliminate spreadsheets, so that when you've got to do some basic conversions from volume fluxes to velocities and that, do it all as expressions, and then it's all documented for you. The other thing, of course, is that these get evaluated and put out in the report. So if I open up the report here, there's a simulation report. It's a bit hard here. If I open up my outline of the report, I've really scrambled up my windows here by doing that. Let me quickly move this open again. One of the things that will come into my report are the expressions. So let me open that back up. The more you try on these windows, the less it succeeds. But you can get all your expressions listed in your report and that. So it's a nice way of actually doing this. So I'll just, I don't know why my mouse is not letting me, but you can see named expressions feature in the reports.